Greetings and welcome to this edition of Material Science Problems. This problem will cover phase transformations, specifically Avrami type kinetics. Avrami type kinetics follow the formula y equals 1 minus e to the k t, and then even the t has an exponent up here, and this all is all an exponent of the e. So what does this all mean? Well, as we have a phase transformation, unlike in the previous chapter, it does not occur seemingly all at once. It will take a while. So we usually plot it on a graph such as this, and we have a value up here of 100%. So in time, once we supercool or superheat our material, it will have a nucleation period in this region, and then some of it will begin to transform. After a while, it will reach its peak of transformation speed. So right here is the fastest amount of transformation. And then as a lot of it's used up, then it peters out, and at some point in time, all of it becomes transformed. At about this point, it is 50% transformed. That's hard to see. There's the yellow. It's about 50% transformed. And this is an important value here, the time to 50% transformation. So this curve here in an Avrami type kinetics follows this particular formula. In our problem, we have a couple of samples that have undergone a certain amount of transformation, and that amount here is 0.2, and so 20% of it has been transformed, and it took 13.1 minutes. We have another sample that is 70% transformed, and it took 29.1 minutes. We're going to use the Avrami equation, and we're going to find out the different parameters for this particular transformation. Now these parameters k and n are part and parcel with this particular material transformation, and we are given also that this is some form of steel and is being transformed at 600 C, and we want to find the percent transformed that is y at 22.8 minutes. So we have 20% done at 13.1 minutes and 70% done at 29.1 minutes. So those are maybe about here. There's our 20%, and here's maybe our 70%. 22.8 is somewhere in the middle here. So, maybe closer to 50%, probably something like that. So, that's where we're shooting for. So we at least have an idea of what we're trying to get with this value. But we can't just plug in 22.8 minutes to this equation again because we don't know the k and we don't know the n. We know the t, we know e, we know 1, and we don't know y. That's what we're trying to find here. So we need to use these values to find k and n. Then we can plug in our time here, evaluate this whole right hand side of the equation, and then find our percent transformed. So to that end, we are going to make two Avrami equations, one for the first set, one for the second set, and solve for k in each of them, set those equal to each other, and then solve finally for n, then go back and solve for k, and then finally answer our question. So our first mission is find k as an expression of n for both samples. Let's start with our Avrami equation. Y equals 1 minus e to the k t to the n, and we're going to solve for k here. So we got y minus 1, so we're going to subtract 1 from both sides, equals negative e to the k t to the n. Going to multiply through by a minus 1 both sides, so these two get switched. 1 minus y equals e to the k t to the n. And then I'm going to take the natural log of both sides. That'll get rid of the e. So I take the natural log of 1 minus y equals just k t to the n. So we've almost got k here. And now I have my expression for k. K equals natural log of 1 minus y. Then I divide that by t to the n. And this is applicable for both of these samples. So now I have an expression here that should apply to both samples. And remember, k is a constant between them. It's the same thing for the entire transformation. And these are two samples of the same transformation. So if I have an expression for k for one, it should be equivalent for the other. So I'm going to take this key expression here and use these two samples for each one. Okay, 1 minus, this is 0.2, so it's 1 minus 0.2 all over time, so 13.1 minutes to the n. And that's going to equal the natural log of 1 minus 0.7 all over 29.1 minutes to the n. And n is the same from both. If I put minutes on the bottom, I can cancel all that out. So all the units are canceled out at this point in time. So I'm going to just evaluate the two tops here. Natural log of 0.8 over 13.1 to the n equals natural log of 0.3 over 29.1 to the n. Great. Now I've got an equation here that has only one unknown. Got n here and n here. Only one unknown. So I'm going to get n by itself on one side. So I'm going to multiply through by 29.1 to the n. And divide through by natural log of 0.8. And I'm going to do that for both sides. So here I will have 29.1 to the n over 13.1 to the n. And that will equal natural log of 0.3 over the natural log of 0.8. Now we could do some things with this, with the properties of logs, but it's just easier to throw it into the calculator and make it happen. But this side we can simplify. Simply have 29.1 divided by 13.1 all to the n, and this evaluates out to 5.40. Okay, so our next thing to do is solve for n again, and I will have to take the log of both sides. I'm just going to use the natural log. So natural log of 29.1 over 13.1 to the n equals the natural log of 5.40. I can easily evaluate this, but n here, because of the properties of exponents and logs, I can put it in front of that natural log. So remember that logs are just ways of using exponents. So if I raise something to a power, or I take the log of something to a power, that's the same thing as multiplying that by that power. We'll just use that here. Go up on the top here, and we've got n times the natural log of, well, we can now evaluate that 29.1 over the 13.1, and that is 2.22. And natural log of 5.40. So now I just need to take this, divide it by that, and I can find my n. So I set n equal to the natural log of 5.40 divided by the natural log of 2.22, and plugging that into the calculator, we can get 2.11. All right, so now we found the second thing that we're trying to do, finding n. The third thing we want to do is find k. Well, this is pretty easy. We already have this expression for k here. So we know that k equals the natural log of 1 minus y over t to the n. Well, we can use either of these data points to plug in here along with our newfound value for n. So let's do that. K equals the natural log of 1 minus 0.20 all over time, which is 13.1 minutes, and that is raised to the n power, which is 2.11, and we get negative 9.8. So that is our value for k. The last thing we need to do here is solve the original question, which is to find the percent transformed. So and this is a steel that has been deformed, and we're trying to recrystallize it. So for this, we just need to plug it into our original Avrami equation. Y equals 1 minus e to the k times t to the n. And that's 1 minus e, and our k is negative 9.8. Our time is 22.8 minutes. Those units cancel out. And it's raised to the n, which is 2.11. Hope this isn't too tricky on your calculator. So we finish up the value of 0.51, which is 51%. So 51% of our sample has recrystallized by the time 22.8 minutes have rolled around. In summary, this problem shows how we can use a fairly simple formula to characterize and predict when a certain percentage of a material has transformed from one phase to another. In this case, we were dealing with a steel simply recrystallizing, and we had two samples. We knew what they would be at 20% and 70%, and we estimated that if we had something in between the 22.8 minutes here, somewhere in between, we'd probably end up with 50%, and that's right about what we got here, 51%. But in order to find that, we had to first solve this equation for k, realizing that k was a constant for both of these data points because they're part of the same transformation, and k and n are transformation dependent. We had this expression for k. Well, we could use this expression for k twice, set them equal to each other, and then find n. Of course, we had to know how to use our log functions first. Once we found n, we plugged that back into our equation for k and found k. Then we could predict any point on this curve for these phase transformations. In this case, we had the value of 22.8 minutes, and we estimated that the total transformation at 22.8 minutes would be 51%. And I hope this helped.